Now it works. Okay, thank you very much for this possibility to be here and to deliver talk to Maxim's next. What I remember, it was previous conference dedicated to his 60th and 50th anniversary. Now the time goes very quickly. So organizers asked me to write on the blackboard. So that's why my talk will be not, you will use huge formulas. So it will be maybe some introduction to the, mainly to the growth of Lie algebras, not on equations, but there are some important relations, and I start with one of them. So I will talk on growth of Lie algebras and general word integrability. I will explain what does it mean. Integrability. And the initial example will be so related to the topic, Klein-Gordon equation. Written in the form, in this form, with some arbitrary function, general situation depending on only on u here. And there is a notion of x integral, which leads to the notion of characteristic Lie algebra of this equation that I would like to recall. So it will be a function depending on u, a derivative, only on derivative with respect to variable x, and so on. Finite number, but we cannot fix here the numbers. And for simplicity algebraic calculations, we denote ux by u1, standard notation, u2, u3, and so on. And this function called x integral if, and of course we consider it's restrict to the solution of this equation that the partial derivative with respect to y vanishes. And in order to how to say, to play with some algebraic stuff in this situation, there are two operators that are considered. First, so-called, yes, but yes, it will be appear right now. So the full derivative that I will denote it by capital D, and this is standard u1. U1. So if you replace u1, put here, not q.
I forgot the restriction is should be such that function f depends on finite number of derivatives.
Yes, finite numbers. So kind of polynomial, but with you can you don't fix the power of this polynomial, and two operators. So this is, if you write, you see this in these variables, then this partial derivative on the functions of this kind, then you see this operator.
I guess that we could write the indices, sub-indices.
Yeah, it was mistake. So now I correct. And now the important thing that I also would like to compute the now in this notation the partial derivative with respect to y, and this is will be df. So it will u partial derivative with u plus, and this. So what we'll have that it will be u1 partial derivatives with y, and then standard calculus, then u2 partial derivatives to y, df du2, and so on. And now you can see that this what we'll have here. U1 is just ux partial derivative to y, and here you get f. This you will give the derivative, which I denoted d capital of f, and so on. Then you have all this stuff, all this tail, and this operator I denote by xf, differential operator. So I remove here f, and then yeah. So you can write formula for it. So it will be f df du u1 plus df u2, and so on, d squared f u3.
That's exactly the first term.
Yes, exactly. You are right. And this condition, it's two conditions instead of that. In order to find this integral, so you ask that this vanishes, this operator, and this tail also annihilates. So you have two conditions. So df you replace dy vanishes, instead of this, then df u 0 and operator xf that I denoted here by this y vanishes. And now the idea of characteristic Lie algebra, that was the days way to Bursa, and then by Sokolov, Shava, and a lot of people. I'm not specialist out of the who was the first and this notion. So the idea is to consider Lie algebra generated by two these operators, and I don't know this except this is partial derivative u by x0. So you have two differential operators, just you formally organize brackets of higher orders, and what algebra, what the algebra you will obtain. And the idea is that if you're looking for x integrals, so you see that it's tangent Lie algebra for the these polynomials, these integrals, or the all operators should vanish at f. And the idea why we should not have fast growth, that in higher floors it will have a lot of operators which okay. Thank you very much. So maybe I lost it some time ago. So I apologize. So and this is the definition. So this is characteristic Lie algebra. And I denote it as it depends on your right-hand part of this equation. I denote it by f. So we are interested in the algebraic properties of this object, and just observation that if I compute the first bracket, so we have two operators, and very natural question, what will have if I compute this commutator? And the answer very simple. It's again the operator of the same structure, but instead of f, you should put derivative with respect to u. So the very simple answer. And we will discuss this property a little bit later. And the first observation, if you are looking for integrable situation, of course, everything is well known here. It's classical. We're discussing in some sense, how to say, contribution to algebra, interesting examples with relations at the moment. Yes.
If, for instance, instead of f of two, write f of u, let's say x, y, it looks like your construction will be precisely the same, just maybe some extension will be.
Yes, 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 yes. And now I am interested. Here is a formal definition. So you see the two operators, one of them written here. Here is, so we have, how to say, formal algebraic situation. So maybe I remove this explanation. Here we have, yes, yes, yes. There are, you can, several variables. So u there is a vector function. So there is can be generalized. So I deal now only with a very simple situation, the most simple. Here, this observation. Now I am just looking for Sine-Gordon equation when f is y. I apologize. I use Russian style of writing hyperbolic functions. So if I consider here, so I compute first commutator, sine hyperbolic sinus u, then next commutator will I have hyperbolic cosine u. You see, and interesting situation that if I proceed again, I take commutator x hyperbolic function again, I return again to the x. So we have, if I, yes, yes. So if I consider the matrix of operator at x0, so it just very simple one, yes. And I want to consider linear span of two operators, just for the moment, not all algebra. So I denote this operator, first one, by x1. This is x2. So three-dimensional subspace generated by three operators. And of course, you see that the idea is to change, instead of operators x1, x2, the eigenvectors. Just to consider eigenvectors of this operator. Hmm? Yes, yes, no, not obvious, but I explain a little bit later. Yes, yes, this is the question. So my proposition, instead of x1, x0, is the same span will be to consider eigenvectors. So x0 will be the same, and here it will be like, remember definition of hyperbolic functions, exponential, and the same it was minus u. And with respect to these operators, it will be simple action, diagonal action, and will be two eigenvectors of x0. And now, if I might, how to say, I'll use the diagrams, how to represent Lie algebras. So I buy bricks. So I use Lego bricks. So the first operator x0, now x1 is exponential, x1, x2, and here it will be x3, their commutator. And the question, what will happen later? What about the growth? How many commutators will have? What will be the structure? So we came to the notion of growth of Lie algebras. Now maybe I remove something from here. Okay, so this is, yes, Sokolov, yes, a lot of people. Growth, yes, yes. And what about growth? So if you let G be infinite dimensional Lie algebra, infinite dimensional. So but generated by finite dimensional subspace by V1 finite dimensional. So V1. It's mistake. Infinite dimensional. Thank you very much. But generation space will be finite dimensional. Yes. And what is the space Vn? So this is span of all commutators of elements. If we can choose basis, some non-standard, just simple way, of length less or equal n. So this is the space Vn. So we can see the double brackets, triple, just up to the order n. And this is, how to say, increasing chain of subspaces. So it's included because it's less or equal. And one can define growth function of our Lie algebra as a dimension of growth function f, which depends on Lie algebra G and the choice of this generated set V1, just dimension of this space Vn. And of course, yes, and of course, V1 we use it because we consider brackets with respect of letters from V1. But it's not well-defined object because it seriously depends on the choice of V1. Here we can, you see then as a generating set, we can see that we started, you see that it was Lie algebra initially generated by two operators, xf and x0. But in this cycle, we'll see that it's more useful to consider Lie algebra generated by three operators, x0, x1, and x2. So it's not in the situation, not canonical choice of finding generators. So it is not well-defined object. So it depends, it seriously depends on the choice of V1. What we have to do? In fact, there is several ways how to eliminate this dependence of V1. Either to consider the equivalences.
It shows that you're going to n plus 1 instead of n.
Yes, yes. This I explained that this example is very special, so this is not a good illustration. But there are some that seriously depends on V1. Yes, so. But the growth in general sense only can be defined. So I'll give you the general definition, classical. What is the growth? So it was theorem by Bergman. That always the limit f v1 g of n power 1 over n always exists limit the power, yes, and I denote this limit by ag, and this limit does not depend on the choice of u1, and the definition is rather simple. So how to say? The definition is there are two possibilities. Either we have exponential growth. So if ag, then exponential growth. And if a G is not power, it's Lie algebra G. One, this is sub-exponential growth. And formally nothing else. But here in the case 2, we have a special situation. If there is a polynomial En such that this growth function V1G of n bounded by this polynomial from n starting with some n large, sufficiently large. So, and in this case, we say that our Lie algebra has polynomial growth. Polynomial growth. Polynomial growth. So it's how to say the general definition, and of course there is another approach used by so-called Gelfand-Kirillov dimension, but it will be next time. So this is exponential, sub-exponential, or maybe polynomial growth. And it was interesting question that whether we have something between here, not polynomial and not exponential, and so-called intermediate growth. Intermediate. No. Less or equal 1. We cannot distinguish. Polynomial. No, sub-exponential. You see, this is a less equal 1. No, it's a. You see that, for example, sub-exponential will be exponential power square root of n. It's also exponential. But here you cannot distinguish the special situation. If you found it's hidden inside, you should present your polynomial. N squared is polynomial growth. It's okay.
N to the power of 29 to the power 1 over n tends to 1. So I mean, it's polynomial growth should be.
Yes. Okay. So 1, but in some situation you have even less than 1. But yes, a special situation. You should present this. There are some examples that may be complicated. Okay, it's complicated. So if you compare with group theory, the famous Grigorchuk example of the group of intermediate growth, it's rather complicated stuff. So, but this is a general situation. I just mentioned that general definition, and we are part. And the group of intermediate growth, Lie algebra for intermediate growth, it's also interesting subject, and I also the first result by Maxim Kontsevich. It was Kontsevich and Kirillov. Kontsevich, Kirillov. And very simple situation. They considered Lie algebra the smooth vector fields on real line. If I take two vector fields on real lines defined by functions x and y, and generate Lie algebra by these two vector fields arbitrarily. What? Of course, yes, you're right. Because one variable, or if it's better even, yes, okay, it doesn't matter. But if you generated by two vector fields on real line, the Lie algebra will always have sub-exponential growth. Or arbitrary, if you take not exponential growth, as your intuition says, it's quite different from the theory of group theory. When you take arbitrary matrices, you will have exponential growth. Here you see the real line sub-exponential growth and sub-exponential growth. Of course, you can take special vector fields, you will obtain polynomial growth. Yes, but in generic situation, if f and g are generic, then we'll have then sub-exponential growth. Not polynomial, okay, not polynomial, non-polynomial. Intermediate growth, okay, it's better to say than intermediate growth. So just example of what can happen if we discuss the growth function. And now return to our first example. So I want to explain what happened with our Lie algebra that we constructed from the very beginning. What will happen, in fact. Maybe I'll give just an answer. So and explain with how to say these pictures by bricks. Just construction of loops of loop algebra, so current Lie algebra. So we consider for simplicity SO3, so our vector product into three-dimensional space, and the formulas, standard formulas, no to everyone, W, U, V, and consider tensor products by some powers of variable t, some parameter t. So the first level I put V, U and V on the odd power. So it will be two elements x1, x2. Here will be W times tensor by t squared. Then again, U tensor t cube, V tensor t cube, again W tensor fourth power, and so on. And here we should add x0, which we have now in the picture. But x0 is a derivation of this Lie algebra. This is x here by this eigenvector with eigenvalue 1. This is -1. This is 0, and so on. So this is derivation. And what about growth? So we'll see a little bit later. So this is this part of this Lie algebra I call positive part. It is proof positive part of Cos-Moody affine in one Lie algebra. So it's centerless, or maybe I should add centerless Cos-Moody. Simplest Cos-Moody Lie algebra was L2. So you see, but I see here instead of SL2 basis considered basis of SO3. So this is isomorphism of this characteristic Lie algebra to this algebra of loops. So this is the answer. This is isomorphism. And now, if we discuss the growth of functions, there is another famous how to say, activity and the direction. It was Victor Katz's conjecture, and was influenced, in fact, at that time, Shabat, Smirnov, and others. And just I recall the history of this, because there is some, how to say, some difficulties, some particularities. So it was conjecture, or in some situation by Victor Katz. So it was Victor Katz. It was 68, and it became theorem by Olivier Mathieu in 1990. And it was the following. So we have Z-graded, simple Z-graded, simple Lie algebra of finite growth in the following sense. Not in that sense I mentioned before. So in Katz's conjecture, it's natural because we have gradient structure. So the dimension of GI is bounded by some polynomials of modular I. So the dimension of this graded homogeneous component is bounded, it has some polynomial. And what was himself, Katz proved the result with some technical restriction, and Olivier Mathieu, he, how to say, removed this technical condition, and the follow the list, the answer was following. So we have 4 groups of Lie algebras, 4 types. So loop algebras of simple Lie algebras. So it is loops. Or here we can say that it twisted loops. So it were Katz-Moody, centerless, Katz-Moody algebras. Here Cartan type, well known. Cartan type Lie algebras, and the struggle was around Virasoro Lie algebra. Virasoro, W, Katz noted, Virasoro Lie algebra. So the history was Katz proved the result with some technical restriction. There was no Virasoro Lie algebra in his list. And Mathieu, he dropped his technical condition, and thus the final result with Virasoro Lie algebra. And this is, you see, there's quite different notion of growth. And the crucial point that is Z-graded simple Lie algebra. It's very serious restriction. No relation, no formal relation. Of course, yes, there are relation, but here absolutely different objects. Yeah. Yes, because stronger, because you see that, for example, we have countably many Lie algebras in this list. This is.
So is this if you have a certain kind of growth?
Yeah. Countably many Lie algebras. So not how to say so many, but the various series restriction hidden in this, it is Z-graded and simple Lie algebras. Here, if we study positively. Here you see that this Lie algebra that we have its positive part, that it's positively graded.
You know, I noticed it surely this last grid. Last grid, where you've written W times 10 to the 4.
it should also include W times 2 to the 6 in the same B, I mean, I don't know, B4 or something. Sorry.
No. So if you say about next time, it will be U times T5 W tensor.
Yeah. You said that commutators of length, fixed sensitivity.
But some of them vanish. If you took a commutator of this one, you obtain this one.
Yes.
Then if you take commutator U with W, you obtain you get here.
Yeah.
No problems here.
Sure, but what if you take commutator of UT cubed with VT cubed? And it is longer. The longest is length is longer.
If you take commutator U with W, you obtain V.
No, you take commutator of UT cubed with VT cubed.
Okay. So you see the rules are the following. So if you commutator of G times M, G2 tensor Tn will have commutator G1 G2 times yes.
You take commutator, say U.
T what power?
Yes, UT with VT cube, you obtain, yes, you obtain W T2, yes, T2, yes, exactly. Correct.
Oh no, everything is correct. Everything is correct. So it is a periodic structure, very interesting. In fact, there is a you see that algebra has a lot of gradings. It's one of them. And this is example of so-called, I often it was some talks of narrow Lie algebras which has homogeneous subspaces of small dimensions. So Shalev-Zelmanov, they propose to consider the width of Lie algebra. So the maximal dimension, if it is bounded by some constant, maximum if it exists, of homogeneous components. So this is example of Lie algebra with 2 formally. And what is important? So, and it was a strong hope at that time that this finite growth seriously restricts your structure of Lie algebras. So they found integral situation related to this Katz list. It was a, how to say, a strong hope that slow growth imply very serious restriction of your Lie algebra. So it can be considered kind of criterion of integrability. But unfortunately, there is no, if you consider characteristic Lie algebras, they have not Z graded, they are non-negatively graded, but their growth is completely determined by the growth of this positive path. Why? Because x0 is all vectors here, the eigenvectors for x0. So the growth will happen only here. So this is the positive part is responsible for the growth. X0 play no role from the point of growth. And what about how many, for instance, Lie algebra? So it was, how to say, classification. So that was my result of 2019. So we try to classify. This is very interesting type of grading. I should mention. So how many? I have time. So I have. You see positively ungraded Lie algebra. So this is strong difference between this situation. So only positive gradings. And it is called Carnot grading. Or Carnot Lie algebra. If G1 with GI gives you GI plus 1 for any I less or equal to 1. So for instance, G1 with G1 gives you G2. So immediately the corollary G1 is generating set of your Lie algebra. G1 generates this type of Lie algebra. Or what is another, how to understand this Lie algebra? So if I consider free Lie algebra generated for finite alphabet, what is the grading for free algebra? The length of commutator, yes? How many letters you have in the words. And this is Carnot grading, because if you consider additional commutators, so you'll give the length increase by 1. What is other example of Carnot graded Lie algebra? So you should have defining relations homogeneous also with respect to the grading of you can, if you have identities, you factorize, yes, Lie algebra. All your identities should be homogeneous. All elements should have the same length. Then you obtain this Carnot grading. And this is play essential role in geometric control theory, and Agrachov, Volodya Sachkov, and many others. And it was the notion introduced by Gromov. It's by Gromov. And of course, you should also have some metric. It will be finite dimensional and some scalar products. And the resulting object is called Carnot-Teodori algebra. So this example is exactly Carnot grading. Yes.
Concerning the example, and if you take an arbitrary finite dimensional simple, the algebra, and construct the corresponding loop algebra, can you say anything general about the growth of this loop algebra?
Yes, it's slow growth. In fact, it's can be derived. I said that it was no direct relation, but from Katz's consideration, yes, it follows that it has slow linear growth. So just I'm going to consider this example. What about the growth of this Lie algebra? So if you have Carnot Lie algebra, so you can define growth function in this specific situation, which is responsible for the growth, because it's a special type Lie algebra. So how to say growth function for Carnot. Lie algebra. So this is the same notation, F, G, and generating set is always G1. And in fact, it is invariant meaning. So it is G1 if I consider our Lie algebra. This is quotient by commutant isomorphic. So this is quite, how to say, no, it's, you can consider by some fixed choice here. Not, they're all equivalent. So this growth function is just sum, what is our bracket? So just sum of dimensional homogeneous components up to dimension n. So this is exactly growth function. It is well defined for the Carnot Lie algebra. It is well defined. And what about our example? Well defined. And this growth function, how to say, you can distinguish, because the classical growth function, you can only take power, Gelfand-Kirillov dimension. So this Lie algebra, you see, this is periodicity 2 by 1. And so in this situation, growth function f, this, how to say, Saint-Gardon, Lie algebra G1, growth with a, like linear growth with coefficient 3/2. And what about the next integral case, Tsarev's equation? Tsarev's. And the structure in the Tsarev's case, it's a little bit more complicated, but also periodical. It's periodical. And this positive part of another affine Lie algebras. Two positive parts. And its growth function is equivalent 4/3n. Yes, Tsarev's means uxy u plus u minus. Yes, exactly. Toda. It's in some sense to the chains related or just some. Yes, I can derive from Cartan matrices, but I have no time. So you see that. So it's Carnot grading for two integrable case. For Liouville equation, we have two-dimensional solvable Lie algebra. Nothing interesting. And what about the how to compare with Katz classification and the list of Lie algebra? So this classification that I mentioned. No. So they're classified not, of course, no Carnot Lie algebras, but with some restrictions. And the restriction is Carnot graded. So just I write GI plus 1, so 1. And the next restriction is that you should, like in this intuition, sum of two neighboring dimensions plus dimension GI plus 1 doesn't exceed 3. So if I have two-dimensional homogeneous subspace like here, so their neighbors should be one-dimensional. This is explanation. So this combination of two neighboring two-dimensional subspace, and even in this situation, this Lie algebras they called narrow by Zelmanov and Shalev. And all of them have linear growth. These are examples that were mentioned. And the answer is the difference between Katz classification when we have countable many Lie algebras in his list. To here we have uncountable set of Lie algebras. So you can realize any combination of blocks here. This is explanation. So you can a lot of them. So yeah. Any diagram of this you can realize by Lie algebras. Yes, obvious continuum of Lie algebras of this time. So this again explains what is the difference between the growth from the classical definition, because there is no Z-graded structure. We cannot, you see that X0, but we have no -1 component. We should X very restrictively. We should have simple Lie algebras. Here it's very simple, very serious restriction. You should have simple Lie algebras. So the morale in Russian. What about moral in this story? So the growth that appears in characteristic Lie algebras of equation is not like in Katz classification. It can you have a lot of different examples, not restrictive. Of course, this two integrable situation, they're related to Cartan matrices. Of course, this is very, very special situation. So Cartan matrix is something, it's not the growth play the role, something more serious. And I promised to say a few words about what about other integrability. In fact, it was the origin of my interest in this situation. So integrability of complex structures. Now I consider not infinite dimensional Lie algebras, but finite dimensional positive graded. They are all nilpotent. Nilpotent, one can consider as corresponding nilpotent Lie group. If it has Lie algebra have rational structure constants, then you have nil manifold compact quotient space with respect to some lattice. And so the question is, what about complex structures? Not general, but left invariant. So if you have not on the group, but on nil manifold, this is very important. Nil manifold. Okay, and what is complex definition? What is complex structure? On okay, nilpotent Lie algebra, nilpotent. Lie algebra G. So we have left invariant complex structure on Lie group. So we have a operator on Lie algebra such that standard definition almost complex structure. And what about integrability condition? So, but Nuremberg theorem said if we consider nil manifold G gamma, it is complex manifold, not Lie group itself, but this quotient nil manifold. Discrete, co-compact. Discrete, co-compact. So this is compact. Compact. The main example, so Heisenberg Lie group of upper triangular matrices, and the lattice is matrices with integers x, y, z. You have x, y, z. Heisenberg. And this is the whole group of Lie algebras and lattice if you consider x, y, z integers. And this is general situation. And this will give you on the quotient if Nuremberg theorem, Müller-Hoissen tensor vanishes. So Gx, Gy, xy. Yes. So this is condition, integrability condition of complex structure. Yes, G more. Yes, G. This is nilpotent Lie group.
G is nilpotent in this theory.
Yes, of course, nil manifold.
I'm just saying that it's not G which is compact, it's the factor thing. Just this arrow looks like G. You're saying G is compact. You're saying G.
No. G is not compact. It is Euclidean space. It's from the point of view of what is manifolds. R3.
I can see that.
Yes.
I'm saying the general theorem says that.
No. Jan, you see that I said that this guy is compact. G is a Lie group. nilpotent, which correspond to Lie algebra G. Nilpotent corresponds to G is tangent Lie algebra. It's tangent. So this is integrability condition for Nil manifold. And you should ask what about complex structure of Lie algebra in the classical sense? The complex structure, then you obtain complex Lie algebra if you have this relation, more simple. You just put out your J from the bracket. This is G is a complex Lie algebra structure. The interesting case that is Lie group itself, it's not complex Lie group. However, its quotient space compact admit complex structure, left invariant. And its integrability comes from Nylander-Nirenberg theorem of integrability of almost complex structure in general situation. And this integrability represents as an Niren-Hayes tensor. And what I would like to finish, what is algebraic counterpart of this? Because it's look a little bit strange. This is Niren-Hayes tensor. So no, here it's equals. No. So it's not zero, it's equals to. It's different. It's equivalent. It's not Niren-Hayes, it's almost. Okay, I put minus here. Okay, and here will be, this is. Okay. So G is okay, so I just, how to say, algebraic condition. So I consider complexification of G. No relation to this complex structure. This is abstract operator acting on real Lie algebra. So this will be complex Lie algebra in the standard way, как complexification as a linear algebra. Then you will get operator G will act in this complex, in this new space. As it is G squared minus ID, it has two eigenvalues, I and minus 1. So G is decomposed Gi plus G minus 1 eigenspaces, eigensubspaces. An interesting fact is this integrability condition represented by Niren-Hayes tensor is equivalent to the following. G plus minus I are subalgebras, are Lie subalgebras. In in GC. So Niren-Hayes, vanishing of Niren-Hayes tensor equivalent that eigenspaces are complex Lie subalgebras.
How is it true that plus corresponds to real part and minus corresponds to purely imaginary part?
Of what?
Of this complex Lie algebra. So you have
no, because you see, this is a formal operation because, in fact, it's how to say, we double the dimension. What is complexification? Here is interesting. Just I want to difference. Okay, maybe it will be explained. What about difference in complex Lie algebra structure? In this situation, if you see that this condition implies this one. If G satisfies this equation, it satisfies this. It's more simple. It's obviously. And here, this situation, this equivalent to the following condition. So in eigensubspaces, G plus minus R are ideals. in GC. One can verify it directly. So this is how to say, this is a restriction of nilpotent Lie algebra, whether it admits complex structure or not. And now I want, how to say, a recent result, not already published. It was classical result that the narrowest possible Lie algebra, which was studied by Michel Verne long time ago, its diagram has very simple structure. So the two-dimensional generating set, and that all one-dimensional homogeneous subspaces. So here we have E1, E2, E3, E4, and only one non-trivial commutator which shifts your vector by one. And this is Lie algebra M0 of n. And it was known, it was one simple observation by Elizabeth Goes that this Lie algebra does not admit any complex structure. Any complex structure. And this is Lie algebra has the slowest possible growth, because its growth like function fn like n is possible. It's all algebras grows faster than this one. So the idea is what is how to say, what are relation between growth. Yes, Michel Verne proved that this is the only one, but with condition it is graded, of course, with Carnot grading. So if this grading is Carnot, then it's the only one. And the interesting situation that in my list, uncountable list of Lie algebras, there is only one Lie algebra which admit complex structure integrable. That exactly we already considered, this one of loops. I recall U tensor by T, V tensor by T, W tensor T squared, and so on. How it takes complex structure as an operator. So just sends this basic vector to this one, it's obvious. This, but here is in this direction. In fact, it just looks like the only one possibility, normal possibility to define operator complex structure, because so it sends to this and in this direction with -1 in order to define complex structure. However, is the only example. Tsarev's Lie algebra does not admit any complex Lie algebra structure. I mean, it's finite quotient. It's finite quotient because you truncate this Lie algebra. So any finite dimensional quotient doesn't admit anything. So the first in this uncountable many of narrow Lie algebras, if you go from this one to this one, so this is the only one with integrable complex structure. And so again, we return to moral. So if you have, the idea was integrable from the point of Darboux integrability or higher symmetries, your characteristic Lie algebra should has slow growth. But in the world of complex structures, quite opposite situation. Your Lie algebra should grow rather faster than. So it's slow. The first your algebra should grow faster than this one in order to have integrable complex structure. And even yes, that result. Yes, there's that result. And in fact, that growth function is useful not only in infinite dimensional case, but only if you study a finite dimensional case, it's also a useful tool. In terms of this growth function, you can just produce this restriction. So this is the answer. So I want to stop now my, how to say, Maxim is not happy now, he's tired. Yes, because I told the things rather far from the mainstream of this conference. But I want to finish with some joke related to mathematics. So I propose to answer the question. Some of them are answered. This is the book on geometry, analytic geometry by, Alexander Petrovich Veselov, Sasha Veselov, is Zhenya Troitsky. Some that know. Yes. And this is the problem is last lecture a few students came to me ask, Dmitry Vladimirovich, can you say something about this picture? What about it? What they are doing? Two people here. So I say just wait a minute, because the problem was just to understand what is the object here, because the table. I am not sure that is. Maybe I can show to the camera in order to involve all people. Yes, and this is classical Albrecht Dürer fort, dated 1525, and then Zhenya Troitsky explained, because he attended School of Arts when he was schoolboy, so he had an interest. And this is instruction by Albrecht Dürer that before Kepler he used his tools. He produced the special book how to draw a picture in perspective, because in that time it was a kind of secret. Dürer himself said that I came to Bologna in order to learn, but I understand they knew how to draw with perspective, but they did not explain to me. And he published the book, and in this book there is 4 tools, mechanical tools, how to draw in the perspective. And I want to ask Maxim to come here. Now we can reproduce this tool, how to Asian artists draw in perspective. So you should participate. So you see that I put this. So what is the object? Object is this вот эта рамка, да, вот она здесь. Frame. And this frame has two fields, как нити, two threads. And you see that on the picture there is another thread that used. This is a picture already made that and is white squared. And this is the picture is called an artist who draw a lute. A lute. So this object is a lute, and this is the picture of a lute. And now we represent this the processes. Unfortunately, I have no lute. But here is you play my assistant. So just imagine here is the lute, and this is the yes to fix. And here the artist asks his assistant to touch special point on his on this lute, on this object he want to draw. Then important thing that here I should have the wall and the fixed point with a грузик. Как груз по-английски, how to say? Weight, yes, as a fixed point in that. So it is not, that is inverse perspective. So I want that way how to draw. And Jan, I need also your assistance. Okay. No, it's a Christmas story. It's not. Maybe you made photograph. No, just one. So just as a practical tool in the time of Dürer, how to draw picture just in mechanical way. Just imagine that Maxima, the artist, asked his assistant to touch specific on the lute. And what I do, this is frame is well fixed, of the table is well fixed. And then what I do? So I have two threads, and you see that.
You realize how clever they were, these people. They managed with just 2.
Yes, I found the intersection point. I realized in this way. And this is how to say vosk. Wax in English. here wax, and then I fix the position of threads by wax. So now you can remove. Just put down. So you see down on the fixed point, and then I put there's a second part of the sheet of paper, and put the point on this. Draw the point of this paper, and you see this is lute already draw with points.
Yeah.
And what is the relation to you, Maxim? This is how to say my some impression of your how to say what you do in mathematics or in life also. Just we found here very interesting point, the intersection point of three straight lines in the space. Then we apply it to some pictures formation. But you have a character. See, this is picture drawn point by point. So you have ability point by point, but to draw a very interesting picture by very complicated computations or often. But the result is, I hope, will be so beautiful, like this lute, which is drawn on the paper. So this is was Christmas part of my talk.